Hello. On this hopefully short video, I'm going to justify the rule for what you do with complex roots and non-real roots of the characteristic equation for a LHODECC. Remember, LHODECC is a linear homogeneous ODE with constant coefficients. All right, and we're going to do that using Euler's formula. Euler's formula says that e to the I theta is equal to cos theta plus I times sine theta. And I is, of course, the imaginary unit. I squared is -1. No real number squared is -1, but I is a complex number, a pure imaginary number, and I squared is -1. I might justify this formula later. It's often done, I'm sure it's in the books, using that Taylor series. I might actually do another video, I'm on a roll here, justifying this formula using differential equations. Why not? Okay, but I can't really talk about this formula without the special case of letting theta equals pi. So I have e to the I pi is equal to cosine of pi plus I sine of pi. And in this class, we never really need to know for what cosine of pi is and sine of pi is, really. All we need is cos of 0 is 1, sine of 0 is 0. But we should be able to know what that is. Cos of pi is -1, sine of pi is 0. So this is e to the I pi is equal to -1 plus 0. Or if I bring this over, I get e to the I pi plus 1 equal, it's a beautiful formula, so I should write it beautifully. E to the I pi plus 1 equals 0. So this is sometimes been called the most beautiful formula ever written. Okay, it's just beautiful. It has all the important numbers. 0 is the most important number, and then comes 1, and then e, and then I, and then pi. It's got all the important numbers in higher mathematics, as well as lower mathematics, like plus sign and equal sign, and numbers 0 and 1. All right. So that's beautiful, but I'm going to erase it. Okay. Suppose I have R equals A plus or minus I B are roots of the characteristic equation. In other words, R1 is A plus IB, and R2 is A minus IB. And we're going to assume that B is positive. A could be 0, and it often is. But B can't be 0. If B is 0, this would be a repeated root. And if B is negative, I just switch them. And so B is positive. We'll assume that. Okay. All right, so I do get two solutions to the ODE. Not just any old ODE, it's a LHODECC. Or I have Y1 is e to the A plus IB times t. And I get Y2 is e to the A minus IB times t. Okay? All right. Now, the rules for exponentials, right? X squared times x cubed is x to the 2 plus 3, right? Same thing happens here. Although we're kind of on steroids here. So this is going to be e to the AT times e to the IBT. And this is going to be e to the AT times e to the minus IBT. So here, I'm going to use theta equals BT. And here I'm going to use theta is negative BT. And I'm going to use the fact that cosine is even and sine is odd. But let's just do this with a BT. I don't have to worry about it. So I get e to the at times cosine of bt plus I sine of bt. And here I get e to the at times cosine of, well, I would put negative bt, but cosine is even, so that's just the same as bt. And I would put sine of negative bt, but sine of negative bt is negative sine of bt. So, oops, so I put a minus sine of bt. And then I need to close that parenthesis. All right, so I've got two solutions, and yes, they are linearly independent solutions to this differential equation, whatever it is that had these roots. And we've talked about that elsewhere. But the problem is they're not real value. They're not the kind of, this is not the droid you're looking for. This is not the solution you're looking for because we wanted a real solution, a real valued solution. It's a complex valued solution. All right. Oh, but look at that. I could take y1 plus y2. If I take y1 plus y2, those terms cancel. And I get twice e to the at times cosine of bt. And that is a real solution. And I take y1 minus y2. I take that minus that. The cosine terms cancel. Oh, and I get I minus minus I get 2I times e to the at times sine of bt. All right. Well, that's not a real valued solution. It's a pure imaginary valued solution. So I have y, I'll call it, I don't know, y sub c of t, standing for cosine, is going to be a half y1 plus y2 over 2 is going to be e to the at cosine of bt. And then I can get rid of that minus sign and that 2 by dividing the difference by 2i. And I'm going to call that ys of t is y1 minus y2 over 2i. And that's going to be, okay, divided by 2i gets rid of that. I get e to the at sine of bt. So I get two real valued solutions to the ODE with those roots. And they're linearly independent, so the general solution is going to be, as we've written out many times, if those are the roots, okay? Those are the roots. The general solution is y is c1 e to the at cos of bt plus c2 e to the at sine of bt. Cool. And yeah, I know one of the things that's kind of confusing about this is the C1 and the C2 we're using here is not the original C1 and C2. Well, I didn't talk about C1 and C2, but right? I have C1 and C2 multiplying any fundamental solution set. Okay? And here's a fundamental solution set. I can even say it right in that way. E to the at cos of bt and e to the at sine of bt. That set of two functions is a fundamental solution set of the ODE. All right. Right, while we're at it, what is the ODE? Just since we're at it, what is the ODE? If with those roots, you might remember. What do? I say r minus a is plus or minus ib. So that's r minus a squared is negative b squared. So the differential equation is going to be d minus a squared plus b squared. All that acting on y is 0. That's the ODE, whose roots are a plus or minus ib. Right? It's a second order ODE. All right. Thanks for listening, and I'll stop this.